Okay. Section 6.1, Everyday Geometry and Applications. The first sentence of this section says, geometry is one of the most useful topics for real life that you will ever study. Yeah, that's a pretty strong statement. I don't disagree. I think maybe the most useful topic in mathematics for real life that you will ever study. Alright. Okay, so first thing we should talk about is some definitions. Some definitions in this section, because this section is going to deal with angles, not really getting into shapes until 6.2. That's the good stuff. Finding area and perimeter, the really, really useful stuff in 6.2. So let's start by talking about the definitions on page. So I'm following the textbook this time because I don't have lecture notes typed up for this section because, well, it's hard to type up lecture notes for a geometry section because of all the pictures. So this is page, it says page 6. What is that? 245. Page 245. Oh, that's just chapter 6. Oh, duh. Okay. So I'm not going to rewrite all of these definitions in this little box here, because you can pause the video, go open your textbook, or log into Hawks and look at your e-textbook and find this. So I'm just going to read along with them and say anything that I think they missed in these definitions. So right off the bat, I want to say something about point. They say a point, first of all, is denoted by an uppercase letter. A point is denoted by an uppercase letter, and it has no length, width, or shape. So it's dimensionless. It has 0 dimension. So if that seems a little abstract to you, it's really not if you just think about it as being a location. Right, it's just a location, and the dot itself is just pointing to or denoting where that location is, where it's marking that location. Okay, a line is a collection of points that extends infinitely in both directions, so it's unbounded in both directions. So we cannot talk about the length of a line because it's just infinite, and it's denoted by 2 points. So 2 points make up a line, and we write it as AB with a little small double-sided arrow subscript above it. Then we have a line segment, which is measurable. It's finite, and so that means we can talk about its length. So we can do a lot more with line segments when it comes to dealing with their lengths and such. And it's denoted pretty much the same way. Two points, except of course no arrow at the end of either side here. And it's denoted with capital AB, just like a line, except there's no arrows on that little bar above it. You probably can't, you definitely cannot see that on video, but if you're looking at the table in your own textbook, you'll see what I'm talking about. And then there's a ray, which has a bounded endpoint and then an unbounded endpoint. Okay, the way we denote it tracks with how we denoted a line and a line segment. So these are all one-dimensional shapes, line segments, and rays, one dimension. And then we have planes, which are two-dimensional. They're two-dimensional planes. Okay. We're not going to do as much with planes in this, but at least note that planes are also denoted by uppercase letters. And points are also denoted by uppercase letters. So whenever you're talking about points and planes, you've got to give some context. You've got to specify which kind of shape you're talking about. well, not shape, but which kind of geometric object you're talking about, whether it's a plane or a point. Okay. So let's do example 1. Again, just following the textbook here. Example 1. Easy enough in example 1. They give us a line segment, which means we have a finite section here that's measurable. KBMC. And we have a lot of different points on this line segment, so we could talk about many different line segments here. I could talk about KB, I could talk about KM or KC, I could talk about BM or BC or MC. And by the way, you can swap the order of the letters here in a line segment. So meaning that KC is the same as CK. So if I was given a problem where I was asked to list every line segment that you can note in this picture, I would not say KC and CK because they're the same. So I wouldn't do it twice. And that's true for lines as well, but it's not true for line segments. Or no, sorry, it's not true for rays. Sorry, I was reading the text. It's true for line segments and lines, but not true for rays, because rays have an unbounded side. So you have to be careful. The order matters in a ray. Now this problem, all it's asking us is, it's giving us these measurements. It says KB is equal to 10 inches. BM is equal to 12 inches. So already that notation is not being used here, and we want the length of KC. And that's because here we're talking about length. We're not noting the line segment KB itself here. If we were, we would draw a little line above it. We're noting instead its length. Okay, so that's an important distinction here. The object itself versus its measure, or its length. Okay, and in this case, obviously, we're talking about the length of each of these pieces. So KB is 10, BM is 12, MC is 13. How long is KC? Well, KC is made up from those three smaller line segments, so KC is going to be, the measure of KC, rather, is 10 plus 12 plus 13. Okay, easy enough. Not too much more to say about that. Okay, so next we have a bunch of definitions coming again with pictures. I'm going to do the same thing. I'm going to tell you where they are, even though if you're already following along, you can't miss them. Hmm, 246 through 247. Okay, so here we're talking about parallel lines, vertexes, angles, acute angles, obtuse angles, right angles, and straight angles. So first of all, I do want to say something right off the bat about parallel lines. So the book is saying two lines, AB and CD, in the same plane are parallel if they never intersect, no matter how far they extend. And then they tell us what is used to denote two parallel lines. And it's those two straight bars. Another way to denote parallel lines, they use those two straight vertical bars, but you may also see it like this. So this would also mean the two lines are parallel. Now, something that they say that you may not have heard before is two lines in the same plane are parallel if they never intersect. The rest of the definition makes sense from there. But you may not have heard in the same plane. So what's that about? Well, it's important to say that the two lines are in the same plane because just consider like space, right? Just floating, lines floating out in space. If I had a line here, floating here, unbounded in both directions, and another line here, right, that's floating above it, technically they're never going to cross, right? They will never cross. If both of these lines were infinite, so use your imagination, they would never cross because one is floating above the other. But that's not really what we think of as being parallel, right? We think of being parallel as they are in the same plane, right? There is no there's no weirdness going on where there's like a vertical distance between them or something like that. And they're in the same plane, but they still don't cross. That's what we want parallel to mean. So that's why there's that little stipulation there in the definition about the two lines needing to be in the same plane, because we don't want this kind of thing to mean parallel. That's something different, right? When they're in the same plane and they're parallel, we can do a lot of different things with them. There's lots of theorems and postulates about two parallel lines in the same plane. Okay, next definition is the vertex. That's the common endpoint, so it's just, let me get a picture here. So the vertex is right there. Typically when we talk about vertex, we're talking about the vertex of an angle, which is exactly what the next definition is. So with an angle, the angle is this geometric object itself. Oops. I notate it the same way they do in the text, ABC. Okay, so when we think of angles, we almost immediately think about their measures, like degree measure, but the angle itself is this geometric object, right? Its measure is how big the degree measure of it is, okay? So this is the angle, and its measure is just how big the angle is. And I'm making a point about that because there's two different notations for those two things. This is angle ABC, and then if I wanted to say angle ABC is 40 degrees, I would say measure of angle ABC. So that little m, meaning measure of, is 40 degrees. So it's not correct to just say angle ABC equals 40 degrees. We have to say measure of angle ABC is 40 degrees. Alright, then we have acute angles, which is an angle that has a measure that's between 0 and 90 degrees. Now, we're not really going to talk about negative angles, so that stipulation about it being greater than 0 degrees is not as important to us. Now, the negative angles exist. An angle can be negative if you're measuring clockwise. It depends on the context of the problem too, though. An obtuse angle has a measure greater than 90 but less than 180. Okay, so that's important to note there. That does matter for us. An obtuse angle is greater than 90, which we probably recall from knowing these definitions from earlier in our math learnings. Okay. Lost my place, got distracted there. Okay, obtuse angles are greater than 90 degrees, got it. Okay, but something like this here, this angle here would be obtuse, but this angle would not be considered obtuse because it's greater than 180. But if I was to measure the opposite side of it, that would be obtuse. But this side would not be because it's greater than 180. An angle that is 180 degrees is called a straight angle, like that, a straight line. Excuse me, a straight line. So any straight line can have a straight angle on it, or does have a straight angle on it. And of course the right angle, which is 90 degrees, which we denote with that little box in the corner, meaning a 90-degree angle. So the measure of this angle, ABC, is 90 degrees. Measure of angle ABC in this problem, or in this picture, is 90 degrees. Okay. Okay, more definitions coming because that's pretty much the how it goes with the first section in this geometry chapter. So we've got adjacent angles, which are just angles that are next to each other. That's what adjacent means, okay? It just means next to. We have opposite angles. So these are definitions on page 248. We have opposite angles, which are exactly what they sound like. They're opposite from one another. And then we have those two important definitions, complementary and supplementary, that we can actually do some problems with, right? Because they say two angles are called complementary if the sum of their measures is 90 degrees, and supplementary if the sum of their measures is 180 degrees. Okay? And then, of course, perpendicular lines. Two lines in the same plane, again, of course, are perpendicular if the angles they meet at is a 90-degree angle. Okay, so example 2 says to determine if the following angles are complementary. So example 2 gives us two angles. Example 2 says the measure of angle ABC is 44 degrees, and the measure of angle EDF is 42 degrees. All we have to do is take their sum and see if it's 90 degrees. If it is, they will be complementary. So 44 degrees plus 42 degrees is of course not 90. It's 86 degrees, so it's not 90 degrees. So they are not complementary. Okay, easy enough. Okay, example 3 is a little bit more interesting, even though it's not using real numbers here. Example 3, so it's this picture with a road and a tree. In the following figure, the road is represented by the line CD, while the trunk of the tree is represented by line AB. So I'm just going to draw those two lines, something like that. There's CD. And then line AB, which is very nearly vertical. Okay. Alright, now if I want to talk about the angles formed by these two lines, I need to notate its vertex there, denote it by something, so I'm going to use the letter E, which is exactly what the picture does. Okay, we want to use the definitions given in Table 3 to show that angle BED is supplementary to angle DEA. So whenever you're asked to show something in geometry, typically, well, there's lots of different techniques, but maybe something that will help here is to think about where you want to end up. You want to show that BED, angle BED, is supplementary to angle DEA. And that means if we worked backwards, so we want angle BED supplementary to angle DEA. But what has to be true about these angles for them to be supplementary? Well, by definition, the measure of angle BED plus the measure of angle DEA has to be equal to 180 degrees. Okay, so we're looking at these two. It's pretty clear, probably, that they will sum to 180, even though we don't know their angle measures. But why is it so clear that they should sum to 180? Well, note that angle BEA is a straight angle. Okay, so we can say angle BEA is a straight angle. And how can we use that? How about we just write that down? Let's say measure of angle BEA is 180 because it's a straight angle. So here is what's going on. These are each of my little points, my little facts that I'm using, well, ending in what I wanted, the goal here. And what's the last step? How do I get these two smaller angles involved with angle BEA? Well, they're adjacent, right? They're sharing this ED side here, right? BED and DEA. They're sharing this side, so they're adjacent, which means that the sum of those two angles, BED, the measure, I should say the sum of their measures, of BED plus the measure of angle DEA should be equal to the measure of angle BEA, because together they form that straight angle. So there we go. So we start off saying the measure of this angle plus the measure of this angle is equal to the measure of this angle. But then we say, wait a second, that's a straight angle, so its measure is 180, which means I can just replace BEA here with 180, but this is exactly the definition of supplementary. We're not going to do a lot of proving things in our class with geometry for several reasons. First of all, it would take a lot more time to talk about, time that I want to give to other things. Second of all, this semester we're doing all online exams and or digital exams rather, and to do something like this on the computer is very difficult. And also, it's just not useful in real life. Like, let's be honest. I mean, the way of thinking, this problem-solving method, is very useful. If you get good at it, it's very useful structure to have to practice in your mind. But there are much more useful, directly useful things in geometry. So I don't want to spend any more time, really, on proving things in geometry. Alright, so example 4, doing some actual calculations here. Alright, so we've got a picture here with several different angles. There's this small angle, this 90-degree angle. Then there's angle ABD, which is also a 90-degree angle. And then there's angle EBC, which is a big old obtuse angle. Then there's the straight angle ABC. Lots of angles going on here, but what we do know is this is a right angle, so BD is cutting this straight angle right in half. And this small angle, ABE, is 37 degrees. And we want the measure of angle EBD. We want the measure of angle EBD, which is this small angle here. A couple different ways we could think about this. We could think about the sum of all three of these angles adding up to 180 degrees, because together they would complete this straight angle. So we could say 37 degrees plus x degrees, so that's the unknown angle, plus 90 degrees should equal 180 degrees, and then we would solve for x. Another way to think about it is 37 degrees plus this small angle should equal 90. They should be complementary to each other. If this angle is 90, then ABD must also be 90. So 37 degrees plus x should be 90. But it's the same thing. It's this equation as if we had just subtracted 90 from both sides, right? If I wrote that down, 37 degrees plus x degrees. So really the same thing. You could argue this way is a little bit easier. Doesn't matter to me. Okay. Solve for x here. X degrees is equal to subtracting 37 from both sides, we're going to get 53 degrees. Okay, cool. Alright, so the rest of this section is getting into some some more angle stuff. Converting decimals to degrees, minutes, seconds. I'm basically done. I am done at this point with this section, but I just want to mention some things that could actually seriously be useful to you in real life. So the whole degrees, minutes, seconds conversion, that's probably never going to be useful. I mean, it depends on what you're doing. If you're in a career path where you're going to be doing a lot of angle measures, I don't know, engineer or something like that, then you'll probably need to know this. Applications, these are fun, but applications of angles, yeah, determining location, that's good, fun stuff, but I'm not going to go over it in detail here, because I don't need you to know it for this class. Here we go. This is stuff that would be super useful to you in real life, though. If you don't know these basic trig functions here, you should take some time to set aside. Again, I'm not going to require you to know it for this class, but these are some of the most useful geometric properties of triangles that you can know. And any calculator, pretty much any calculator can do it. Maybe not like a desk calculator, but a scientific calculator can run these calculations. Basically, all it does is it relates the angle measure inside of a right triangle to its side measures. That's all these three functions are doing. Sine, cosine, and tangent, that's all they're doing. They're relating the angle measure, which is the capital A, to the ratio of the sides. And this can help you find, you know, the height of a tree, if you know the angle measure to the top of the tree, which is something you can measure on the ground. And yeah, all sorts of different applications there in real life. And the rest of this section is just more trigonometry. Cool. Alright, that's it for this section.